What I'm going to talk about here is some of the basic definitions, vocabulary and symbology associated with proofs and some of the work that we're going to do when we're looking at number theory. Now we need to be aware of some of the definitions associated with it and what some of the symbols that we're going to come up against mean in relation to the material that they present in each of the cases. First thing we need to know though is what the most basic premise associated with proofs are, and that's statements. Now a statement is any sentence which is either true or false but not both. So 3 plus 5 is 4, that's a false statement. 4 plus 5 is greater than 10, that is also a false statement. 2x plus 3x equals 5 is true. Each of those statements is either true or false, but neither both. And the negation of a statement is usually constructed by putting the word not after the verb of a sentence. So if a statement is true, its negation will be false, and vice versa in any sentence which is either true or false, but not both. So looking back at the previous ones, 3 plus 5 does not equal 4 is true. 4 plus 5 is less than or equal to 10 is true. 2x plus 3x does not equal 5 is false. So each of them have flipped by just putting the word not or changing the condition going from being greater than to less than or equal to and flipping that around. So the negation changes the meaning of a statement completely. We also can make compound statements. Now these can be formed using given statements and combining them in different ways using a different variety of vocabulary and various words and phrases associated with it. So we can use the word and. So for example, I could say 3 plus 5 equals 4 and 4 plus 5 is greater than 10. Now that is false because if and joins the statements, it's only true if both of them are true. And neither of them are true, so it's false. I could use the word or. So 3 plus 5 equals 4 or 4 plus 5 is greater than 10. Now that is false because if or joins the statements, the compound statement is only true when at least one of the statements themselves are true. So if I'd said 4 plus 5 is less than or equal to 10, that would have made the overall compound statement true because one of them would have been true. The last one I can do is use if then. So I could say if 3 plus 5 equals 4, then 4 plus 5 is greater than 10. And that would be true because when if and then is used, the statements are false only when the first statement is true and the second statement is false. Now you're probably looking at it going, well, if that's true, then how can that be? Well, if 3 plus 5 equals 4, and I assume that's true, 4 plus 5 then becomes 3 plus 5 plus 5, because I can use the 3 plus 5 to represent the 4. So that then becomes 3 plus 5 plus 5, which is 13, which is greater than 10. So it's true. So the first statement is true and the second is false isn't the case. In this one, what I've said is the first statement is true, the if, use that in the second statement, which makes the overall statement true. Now a good way to represent these would be using truth tables. So if I stuck with the statements I just discussed and represented it using a truth table, there's 4 possible ways it could have them combined. So A and B could both be true, A could be true, B could be false, A could be false, B could be true, both could be false. And each of those, depending on the vocabulary I used to link them, would have different outcomes overall. So for example, with them both being true, not A or not B would be false, because it is A and it is B, they're both true. A and B, A or B, and if A then B, all 3 of those would be true. Because A and B are both true, they all work out. Now if I was to look at A being true and B being false, not A would be false, but not B would be true, because it is not B, whatever that property may be. If I was using and said A and B, that would overall be false, because I would need both of them. If I was to say A or B, that would be true because A is true. Despite B not being true, A is true. And if I was to say if A then B, that would be false, because A is true but B is false after that. If I was to flip it and say A is false, B is true, not A would be true and not B would be false, which would mean that if I was to look at the rest of it, A and B would be false, A or B would be true because B is true, and if A then B would overall be true. Now you're thinking to yourself, how's that? Well, think of the previous statement. I said if 3 plus 5 equals 4, then 4 plus 5 is greater than 10. Well, 3 plus 5 equals 4, that is a false statement. But if that were to be true and I substituted it in, that made B true. So it made the second statement true, which meant that overall it was actually true despite it being a misleading statement to start with. And the last condition here is if A and B are both false. Well, we know not A and not B would be true. A and B would be false, A or B would be false, and if A then B would be true. Because if one statement's false and the other statement's false because of that, overall it would be true. So if A was false, then B is false. That is true in this scenario. And from this you can see that if two statements have the same truth, then the statements are logically equivalent to one another. Now, we've got what's called a universal statement. Now, this refers to all the items in one of the sets of numbers that we have. So go away and remind yourself of sets of numbers. So, for example, 2x plus cx equals 5x for all x belonging to the real numbers. X squared plus 1 is odd for all x belonging to z, which is the group of integers. And an existential statement states that there exists at least one item that has a special property. So for example, there exists an x such that 2x plus dx does not equal 5x. There exists an x such that x squared plus 1 is odd. So they refer to a single item. So they refer to a single x for each of them to satisfy it. Now they may not satisfy it, but the existential statement refers to just one numerical value or one element from the group. Now we can also have related implications, so let's go back and think about the if-then statement. Now this is often referred to as an implication, and a popular example of this is Pythagoras' theorem. So if the triangle ABC is right-angled, then c squared equals a squared plus b squared. That there's an if-then statement that has an implication that is true. Now there's three different ways that we can have it. We can have the inverse, the converse, or the contrapositive. So we can say, if the triangle ABC is not right-angled at C, then C squared does not equal A squared plus B squared. So we can change that round and look at it from the other side of it, so the inverse of it. We could look at the converse, so just rearranging the statement. So if C squared equals A squared plus B squared, then the triangle ABC is right-angled. And we could look at the contrapositive, which is looking at it from a totally different perspective. And in this case, saying the contrapositive would be if c squared does not equal a squared plus b squared, then the triangle ABC is not right-angled. So it's essentially looking at a different perspective but using the inverse statement to get where we're looking at it from. And there's a couple of things to note about this. In any case, only true implying false is false. So if we make a statement and actually we end up getting a false result for that statement, it's false overall. And the truth tables for the original and the contrapositive are the same, meaning they're logically equivalent. Something that we can remember when looking at using proof by contrapositive when we're proving statements in scenarios. And the third thing I want you to remember is that if the original implication is true, the inverse and converse need not be true. So the original statement might be true, but the inverse and the converse, it doesn't guarantee they'll be true. They may be true, they may be false, so don't take it for granted when it comes to that. Now, the last thing I want to talk about is the phrases necessary and sufficient. Now, when we're working with it, there's a couple of symbols that we should really bear in mind. The first is this. Now, what this means is for all values of. So if I were to look at this here and write it in this format, that would mean for all values of x. So for all values of x, 2x plus the x equals 5x, that would be the same as writing it in this format. So for all x, 2x plus the x equals 5x. This here, what you would look at and think is a backwards capital E, means there exists. So what we would be able to do is this here would mean there exists an x. So I could take the statement that says there exists an x such that 2x plus the x equals 5x. That would be the same as writing it like this. So there exists such that st this. This symbol here means implies that. So this statement implies the next statement, implies the next statement. We could use that to follow the truths as we work through something and follow the assumptions that we're making. And as each assumption is true, that leads us on to the next truth, which could lead us on to the next truth, and be a good set of steps for us to follow when we're working through proofs. And this symbol here with the arrows on each end is often read as if and only if. So this is a two-way implication or equivalence. Yeah. So for example, x squared is even if and only if x is also even. That could be a statement that we'd be able to write. So we could write it, for example, as x squared is even if and only if x is even. Alright, so let's consider these statements here. So first statement here, for n to be divisible by 4, it is necessary that it is divisible by 2. For n to be divisible by 4, it is sufficient that it is divisible by 2. Now what that means is if we look at each of these, we can notice the difference between necessary and sufficient. So this first one here, necessary, means it must be. So for something to be divisible by 4, it must be divisible by 2. Well, this is true because we know that 4 is equal to 2 times 2. So any number that has 4 times it, so let's say 4 times a, that's going to be the equivalent of 2 times 2a, which is equal to 2 times m, where m is equal to 2a. So it's necessary that we're able to divide it by 2. However, saying it's sufficient that it is divisible by 2 is not the same. Because, for example, if we take 6, we know that 6 is 2 times 3. So if we say it's sufficient that it's divisible by 2 for it to be divisible by 4, what that means is if we take it to be that, we can divide it by 2 here, but we know it can also be divided by 3, and there's no way that 6 appears in the 4 times table. So a number that takes the format of 6a is not divisible by 4. So we have to make sure we get the difference between a necessary statement and a sufficient statement. They can completely change the meaning of something, and they can have totally different impacts on the overall situation that we're looking at. Now these are just some of the, ironically, necessary conditions, symbols, and terminology that are associated with direct and indirect proofs that we need to be aware of and work with. Because we see them come up all the time, and we have to be able to use them effectively ourselves in order to communicate our situations effectively, communicate our answers clearly, and be able to explain exactly what we've done, how we've got there, and most importantly, what does it mean.